Hi everyone, in this video we're going to be talking about polynomial and rational inequalities. So we are going to be solving both of these inequalities. Alright, so our first example, we're going to solve a polynomial inequality using a graph. And so we're going to be solving x plus 4 times x minus 3 squared greater than 0. And we're going to solve that by graphing the function, which is this polynomial function here, with the equal sign instead of our inequality symbol. And so we're going to use techniques in the past for how to graph this, and then we'll at the end look at when is this function or graph greater than 0. Okay, so graphing this function, it's already factored for us, so let's talk about a little bit of the things that are going to go into the graph. We have our zeros or x-intercepts when we set each factor equal to 0, and so we're going to have an x-intercept at -4 and also -4, 0 technically, and also at 3, 0, and that's from these two factors here. And then if you notice, the multiplicity on this factor for this real 0 is invisible 1, so this is going to be what's called a cross point. We're going to cross through this point, and then the multiplicity here is 2 on this 0, this real 0, and so that one is an even multiplicity, and we call that a touch point. These are all things that we previously learned on graphing polynomial functions. So we have that so far, and then also let's go ahead and just find the y-intercept. So real quick, if you plug in 0 for x, you're going to get 36. So this is 0, 36 for our y-intercept. And then let's talk about the end behavior of this function so that we can go ahead and graph this. And then we have, if you notice, x plus 4 times x minus 3 squared. But if you just focus on the x's, think about what you have. You have x to the first power times x squared. So if we get rid of all the extra stuff, this function behaves like the power function x to the third. So the behavior of this graph when we go toward the infinities, the ends, the left and the right of the graph, it behaves like x to the third. And also, the last thing before we graph this is that there's a positive leading coefficient. There's a positive invisible 1 out front. And so that's going to be, let's just write that down, positive leading coefficient. So that means that our function, for an odd function, it's going to go down left and up to the right at the ends. Okay, so putting all this together, we'll go ahead and graph our function. Okay, so here is what the function looks like. Notice our end behavior. This goes down to the left, up to the right. We cross through the x-axis at -4. We just touch the x-axis at 3, and we bounce back up. And then we have our y-intercept here at 0.36. And so with that information, we can put this together to get the blue graph. And then you can just find a few additional points. This one's an additional point right here at -250. And here's another additional point at 536, just to make this more accurate. Okay, so again, we learned how to graph the polynomial functions in the past, but what we're doing today is we're focusing on inequalities. So when is that function greater than 0? So greater than 0 means above the x-axis. And so for us, if you take a look, if you just say, okay, anything above the x-axis is greater than 0, I want that part of the graph as my answer. And so if you notice when that starts, it starts right here at -4. Everything is above the x-axis. It actually stops right here at 3 because this is touching 0. And then we have to start again after 3. We're above the x-axis. So anything from -4 in between here, from -4 to 3, and then again after 3. So that's what this looks like as a set or interval notation. Just saying that we're jumping over 3 because technically it's not greater than 0, which is what we want. Okay, let's go ahead and try another one. So solve this inequality. X to the 5th is greater than -x squared algebraically. Okay, so first let's go ahead and rearrange what this looks like by moving all of our terms to one side. So if you add x squared to both sides, you have now that the right side is going to say greater than 0. So we're going to work on this version of our inequality. Okay, so next step is going to be to find the real zeros. And this function here, if we put an equal sign for now, because it wasn't an inequality, but we're setting it equal to 0 for now, we're going to look for the real zeros. It's not factored, so we actually want to factor this. So first thing I would say is notice that you can factor out a common factor. Both of the terms have an x squared. So if you factor that out, you have x cubed plus 1. And if you ever want to check, you could just redistribute, and then you'll get back right where you started from. Okay, and now this one factors even further, and I'll remind you of how this one goes. But x cubed plus 1 is what's called the sum of cubes. So a reminder, if from your previous algebra days, this is a formula for the sum of cubes. So if you have something cubed to the third power plus something cubed, it always is going to factor like this. So if it's a cubed plus b cubed, you have a plus b times a squared minus a times b plus b squared. That is the sum of cubes factoring. There's a very similar formula, and I might as well show you right now, since we're talking about it, called the difference of cubes formula. And it's almost identical, but your signs do change. It's a minus b here, and then a squared plus ab, and then plus b squared. So you might want to add those to your notes, just so you have those handy for factoring when it comes up in the future. Okay, so now we factored x cubed plus 1 as this right here. And if the product of all of these factors equals 0, then we can say, well, then the first factor is 0, or the second factor is 0, or the third factor is 0. And then we solve each one. So the first one, you get x is 0. The second one, you get x is negative 1. And on the third one, if you try to factor this or use the quadratic formula, you would get an imaginary number. So this one doesn't have any real solutions. So these two are going to be our only real zeros. Okay, so our x-intercepts for our graph. Okay, so now we're going to go ahead and use those zeros, we call them real zeros or roots, also called roots, to separate our number line and pick some numbers around those numbers that we found to figure out which part of the real numbers, the number line, satisfy our inequality. Okay, so let me show you what I'm talking about. All you do is draw a number line. Okay, think of it as your x-axis, and then you want to mark important numbers, like the numbers you found. 0 was one of them, and negative 1 was the other one. And then you just want to pick some numbers around them. Okay, so if I divvy up this number line here, I want to pick something smaller than negative 1, so let's go ahead and pick negative 2. And we plug that into our function. And if you plug that into the function and you simplify, you get negative 28. Okay, in between our real zeros, so in between negative 1 and 0, you want to pick something. Doesn't really matter what you pick. In this case, it's not really nice numbers to choose from, so we'll pick the fraction negative 1/2, plug that into our function, and we get 7/32. Last one. On the right of 0, pick something. I'm going to go ahead and just pick 1, and if I plug in 1 into the function, we're going to get out 2. And so what you're interested in is whether or not the answer, when you plugged in those numbers, was negative or positive, because that's all you need to know to answer the inequality for the function. And so the inequality was saying, when is that function greater than 0? And anything positive is greater than 0. So positive is greater than 0. We know that negative, anything negative, would be less than 0. So we want all the positive numbers, and based on that table we just made, we figured out that anything that was between negative 1 and 0 was positive, and also anything bigger than 0 was positive when we plugged them in. And so then our answer in interval notation is from negative 1 to 0, and then from 0 to infinity. Just to sum that up really quick with what we saw on the previous slide, we had picked numbers on the left of -1, in between -1 and 0, and then on the right. So we picked numbers here, here, and here. And it turned out that this was negative, so we don't want the number over there. But in here was positive, and over here was positive. So we want any number, let's just change the color really quick. We want any number in between -1 and 0, and then also we want any number greater than 0. And that's why this is the answer. Okay? And we don't include 0, we have to jump over 0, kind of like this, because there's strictly greater than 0. We don't want to equal it. It was strictly greater than, there was no equal bar there. Okay, so then this is what it looks like a little bit more clear on the number line. Using parentheses, because there's no equal bar. So we've talked about this before, but parentheses when you have strictly less than or greater than, and brackets if you have the equal bars on your inequalities. Okay, so parentheses, anything between -1 and 0, jump over 0, parentheses, anything from 0 all the way to infinity. Okay, let's keep going. So now we're going to focus on rational inequalities, and we're going to solve this one by graphing. So again, this is going to rely on some past techniques that we've used for graphing. So we'll go through it kind of quickly, but we will go through it again just to review with you. So we're going to change this inequality into a function with the equal sign here for just some time to graph. And then we'll, at the end, we'll go ahead and remember that this was actually an inequality. Okay, so we're going to determine when is it going to be above the x-axis at the end, because that's what's going to satisfy this inequality. Greater than or equal to 0, so above or touching the x-axis. Okay, so here is the graph. So it's already done here, but let's go through what happened. Okay, so this was our function, and again, this is things we've done before, but let's talk about it. If you have your rational function here, you have asymptotes. So remember from the past, your vertical asymptotes occur when your function's undefined. So in this case, it's when the bottom is 0. So when the denominator is 0, this would be undefined, and we would have our vertical asymptotes. So notice what numbers make that true. It would be when x is positive or -3. So that is why we have our vertical asymptotes here and here. Next, remember your horizontal asymptotes. Those ones occur when you look at the degrees on the function, and then it depends on the case that you're working with. So in this case, we have degree 1 on top and degree 2 on bottom. And so because the degree on top is less than the degree on bottom, then that means that there is a horizontal asymptote at the line y equals 0. Anytime the degree on top is less than the degree on bottom. So that's this one here. Okay, so notice that that's the horizontal asymptote. All right, and then to get the rest of the graph, once you have the asymptotes, you want to just plug in a few points. So it usually is helpful to find your x-intercepts. So for our function, if we find our x-intercepts, so if you set the function equal to 0 and you solve, you would end up multiplying the denominator out. It would be timesing by 0, and you would get x minus 1 equals 0. So that's why your x-intercept is at 1 right here. And your y-intercept, plug in 0 for x, and you would get -1 on top, -9 on bottom. So that's why you have a y-intercept at 1/9, very low right there, close to 0. And then the rest of the points you can find by just plugging some numbers in. So what do? And this is a technique we used in the past, is you take your number line and you say, well, I have an asymptote here, I have a vertical asymptote here. Let me pick some number to the left of that asymptote, pick some number in the middle, and pick another number over here to the right. And you just plug them into your function and you see what it equals. So on our graph, we picked -4, and we figured out that that equals -5/7, and we plot that point. In the middle, we already had 2 points, but if you wanted to pick a third one, we picked 2, plug it into your function, and it equaled -1/5. And then over here on the right, something bigger than 3, we pick 4, plug it into the function, it equaled 3/7. Now once you have all those points, what you want to do is just follow your asymptotes. So you say, okay, I know that I have a point here, and so I'm going to approach this horizontal asymptote, and I'm going to approach this vertical asymptote. And you do that for the rest of the points. One last thing to mention for the graphing part of this is the fact that you do cross the horizontal asymptote. And so this is sort of a side step, but it is interesting and important to consider. So if you cross your horizontal asymptote, all you do to figure this one out is you set your asymptote. So for us, you set this equal to your function, and you see if it's going to ever be true. And we've already figured out that it was. It happened when x was 1. So that's how we know that this was a point where we're going to cross through. Okay, so there's the graph. So that's a quick review on graphing rational functions. But now back to what the question was really asking. When is that function greater than or equal to 0? So greater than or equal to 0, let's change the color here, is going to be touching or above the x-axis. So anything touching or above the x-axis. And so notice when this happens, we touch right here at 1. So this is at 1, and it's above, okay, it's above to the left of that. So it's all above here. And over on the left of -3, it's down below. So starting at -3 all the way until 1, so in between here and here, we're above the x-axis, and we're actually touching it at 1. And then again after 3 over here and going all the way this way, we are again above the x-axis. And so those are going to be the parts that we want to solve, to say that's our answer for our inequality. And so here is our answer as a set. We have the set of all x's such that x is between -3 and 1, and x is greater than 3. But notice we have a bracket or equal bar on 1. And so when we write this in interval notation, we have from -3 to 1 with a bracket on the 1, and then from 3 to infinity with parentheses. Alright, let's do one more. So we're going to be solving this inequality algebraically this time, not graphing. And then this one we're going to want 0 on one side, and so we're going to have to do some algebra to rearrange this. So we're going to move over the 2 by subtracting, so subtract 2 from both sides, and also go ahead and expand the denominator so you can FOIL that out. So real quick, if you want to see that, you would just say x plus 1 times itself, and then you would FOIL that out. So first times first, outer times outer, inner times inner, and last times last. That's where x squared plus 2x plus 1 came from. And then if we want to combine these two terms, we need a common denominator. So remember how fractions work. You can only add them if you have a common denominator. So if you had something like this, like 2 fractions, you can put them together if the denominator is the same. We call that a least common denominator. And so to include this -2 when we subtract it and put it together with what we had over there, we're multiplying the top and bottom, the 2 technically, by this common denominator over here. So this is really like the number 1. Anything times over itself is like the number 1. So we are allowed to multiply by this. So we're going to multiply this by 2. And so technically you're going to distribute the -2 on top, and then keep that common denominator. Okay, so once you have the common denominator, just like we did back here, you can go ahead and combine the numerators. So notice you still had your 2x squared plus 5x plus 6. But then if you distribute the -2, you have -2 times x squared, which is here, -2 times 2x, which is -4x, and negative 2 times 1, which is negative 2. So that's where all that came from. Now this looks ugly, but that's okay. Watch what happens if we combine like terms. You have 5x, let's go change colors really quick. You have 5x minus 4x, so that's 1x. You have 6 minus 2, so that's 4. And then you have 2x squared minus 2x squared, so those are gone. So here's what it really looks like. So if you factor the bottom back out, it's x plus 1 squared. The top was just x plus 4 after we simplified. And so now we're ready to go forward and say, well, what are the real zeros of this function? And at the end, we'll answer when is it greater than or equal to 0. Okay, so if we have the numerator set equal to 0 or the whole function equal to 0, that's going to tell us our real zeros are our roots. So if you just set this equal to 0 and solve, that's where you're going to get negative 4. And then you want to pay attention that the function is actually undefined when x is negative 1. So no matter what we end up getting at the end, x cannot be negative 1, because if you do plug that in here, the whole thing's going to be divided by 0, which is undefined. Alright, so we're going to split up our number line, our real number line, with our real 0, negative 4, and also the number where we can't plug in, where the function's undefined. And so we're going to find a number to the left of negative 4, pick a number in between negative 4 and negative 1, and then pick a number greater than negative 1, and then see how our function behaves and if it's positive or 0, greater than or equal to 0. Okay, so splitting up our number line here, and then picking numbers. So notice the minor difference, but we have a point that we're going to end up including because we can equal negative 4 in our intervals, but this one's an open circle, which lets us know that we cannot include it because remember x cannot be negative 1, so that one's always going to get a parenthesis when we write our interval notation at the end. Okay, so something smaller than negative 4, if you just split up your number line here, pick something smaller than negative 4, we'll pick negative 6, plug that into the function, and you get a negative 2 over 25, and it's a negative answer. Pick something in between negative 4 and negative 1, we'll go ahead and pick negative 2, plug that into the function, we'll get positive 2, and something bigger than negative 1, we'll go ahead and pick 0, plug that into the function, and we'll get positive 4. And then we use that to answer our final answer. So our whole function is greater than or equal to 0, so positive, remember we were looking for greater than or equal to 0, so those were positive outputs, or 0, because you can include 0 because of the equal bar here. And so that happened when we chose numbers between negative 4 and negative 1. And then that was also positive numbers that we got out when we picked numbers greater than negative 1. And now we can equal the negative 4, but remember we cannot plug in negative 1, so make sure that we don't include that into our answer because the whole function was undefined at that point. And so our final answer in interval notation is anything from negative 4 to negative 1. You can equal the negative 4, that's why there's a bracket, but you cannot equal the negative 1, that's why there's a parenthesis. And we jump over the negative 1, and we can plug in anything after that all the way to infinity. And all of that, if we want to just check, we can plug those numbers back into our inequality, and it will be greater than or equal to 2. So let's just pick a number really quick. Let's go ahead and pick a nice easy number. Right here in this interval, we'll pick 0. So if x is 0, let's plug it into our inequality originally. So that's 2 times 0 squared plus 5 times 0 plus 6 over 0 plus 1 quantity squared. So on top, that's going to be 6. On bottom, that's going to be 1. And so 6 is greater than or equal to 2. So that works. So just proving that we did in fact find the right intervals where the numbers exist, and when we pick them from those intervals, they will satisfy this inequality. Okay, so we solved both rational and polynomial inequalities, and we did it in 2 different ways, graphically and algebraically. So that's it. Thanks for watching.